Well, thank you so much for joining us this evening. It's great to see so much interest in cutting edge science and support for the Aspen Center for Physics. I guess the theme of my extremely short introduction is that sometimes things develop slowly and gradually, and sometimes they just burst onto the scene. So, for example, here we are at this conference that's being held during this week. So there's something like 100 scientists and also members of newly founded industry, the quantum computing industry, who are here in Aspen this week. And they are paying attention and learning about a rapid new technological development, which our speaker will do a great job of introducing, where now we can start thinking about building a quantum computer where the bits of that computer are not something stashed inside of an iPhone or a laptop as we know it today, but are actually just single atoms that are floating in a evacuated chamber and suspended there by light beams with the power of about as much as a laser pointer. So that's the sudden thing that's burst on the scene. And hopefully as you walked in, and maybe also as you walked out, you'll be able to see the posters that people have put up and left on the walls and are the center of our discussion during breaks and such. And you'll see really the really exciting developments that are defining the future. At the same time, things develop kind of slowly and gradually. So one of the fabulous things that the Aspen Center for Physics does and has done for a long time now is it allows scientists to get to know each other at all sorts of stages of their lives and not just work together intensively like we're doing here at this meeting, but also, to go skiing or to go hiking and to also bring our families in and to get to know one another. Those kinds of contacts that we form here at the Aspen Center for Physics, let's say today, will have an influence on the scientific trajectory and the career and the lives of the people that have come to these meetings for the next decades. So that then also brings me to introducing Vladan. So I have known Vladan Vuletić for a long time, maybe about 25 years or so. And it's one of those things when you meet somebody for the first time, you have to have this perspective, at least in science, you have to have this perspective that this person you're meeting, peer, may be your peer and colleague for the entirety of the rest of your life. So you'd better be rather nice. Fortunately, Vladan is always very nice, so he was forgiving of whatever I might have said. But we met each other as we were both at that time sort of searching for faculty positions. And Vladan was already a very accomplished scientist at that point. He'd done some really fabulous work, which was teaching us new ways to cool atoms down to very, very low temperatures. Some manifestations of that work are actually what powers this kind of approach to quantum computing today. And in the years since, Vladan has been on the faculty first at Stanford University and then at MIT, and you could read his bio in the little brochure that you received. But I'll just say that, over the years, my admiration for him has been steady and has grown because he's just one of those scientists that sort of sees through the fog and sees things clearly, also can identify new directions and new opportunities. And I find myself, whenever I go in some new scientific direction, I'm often looking up papers that Vladan has written 2 or 3 years ago to kind of light the way. And he seems to be able to do it perennially, including with the developments that he'll speak about today. So with that, let me welcome Vladan to his public address.
Thank you so much, Dan, for the very, very kind introduction. And yes, I look back with fondness on those years when we applied in the same year for faculty positions and had a very friendly relationship then. I would like to tell you about the mysteries of quantum mechanics and how they relate to quantum computing. And in particular, what you see here on this screen is not a cartoon, but an actual camera image where each of these dark green spots is actually one single atom, can be controlled and addressed and sorted in these patterns. You should think of this as a quantum processor that can process quantum information. These atoms are at extremely low temperatures, only a millionth of a degree or so, a few millionth of a degree above absolute zero, and they move very, very slowly, which means that they can trap in trapped in laser light. And the reason why they are so nicely arranged is because there's not a visible beam here, but each of these atoms is trapped in a tiny beam. And that's what I would like to tell you about. So there's a lot of excitement about quantum. What is it all about? You may have seen the headline, Race to Quantum Computing. I got a little bit nervous when I watched the presidential debate, and then Kamala Harris started talking about quantum computing as a future technology. Why am I worried? Well, because that's a large expectation, and also I think things need to evolve in a natural way. We are just trying to build systems, and we would like to give you a realistic perspective, maybe not with too much hype, about where the field is going. So the thing I would like to tell you about is about the foundation of entanglement. This is what lies behind the potential power of quantum computing. I will tell you about what Einstein didn't like about it, the famous Einstein-Podolsky-Rosen paradox, and how John Bell figured out a way to actually test this. The first experiments that were done with photons, and then how we switched to atoms, where this, rather than studying the entanglement foundations of quantum mechanics, we now use quantum mechanics as a tool to accomplish other things. Quantum mechanics has two essential features. One is that you can be in two or more places at the same time, as illustrated in this cartoon. So in quantum mechanics, I can both stand here or over here at the same time, not or, but and in some way. This is the famous Schrödinger's cat paradox, where he imagined the cat being simultaneously dead and alive. And of course, it's absurd because we know that in our classical world, never see something like this, where the skier passes on the left side and on the right side simultaneously. But in quantum mechanics, that can happen. That, however, in some sense, is maybe the smaller of the two mysteries of quantum mechanics. The bigger mystery is the fact that not only can particles be in states at once, but they can also have correlations with one another. They can, the state of one particle can depend on another particle in a rather complicated way. So this is a kind of illustration which says that, if these were classical bits, if this was stored in the computer, you could store a certain number of combinations, but each of these can now be in a superposition of two different states. And it turns out that the number of possibilities of this system grows exponentially. Exponentially is very hard for us to imagine as humans. Imagine something bigger, then it's even bigger. So imagine, for instance, 300 qubits, just 300 particles in a superposition of two states. If you wanted to store this state, you couldn't store it in a computer. In fact, you couldn't store it in the whole universe because there would be more states of this 300 qubit system than are particles in the universe. Okay, it's really hard for us to comprehend. Quantum mechanics is very special because even though we can have all these possibilities, in the end, we have restrictions on what we can measure. And that makes it interesting and complicated. So what was Einstein's problem with quantum mechanics? He imagined an experiment that had to do with correlations. He imagined an experiment where you had some source of particles, and this source was shooting out particles. The particles would have an undefined momentum, and associated with that, undefined position. So basically, if you measured one of these two particles, depending on whether you measured the position, for instance, you measured the position, you would find it each time you tried in a different location. Or if you decided to measure momentum, you would find different values of the particles' momentum or velocity. But what you would find is that the particles would be very strongly correlated. At least in quantum mechanics, you could write down such a state. Meaning, as soon as I measure, for instance, this particle 2 in position, I know exactly where particle 1 will be. And if I instead measure the velocity of particle 2, I know exactly what the velocity of particle 2 will be. But for instance, if I measure the velocity of particle 2, I won't know anything about the position. So this feature of entanglement is this feature that if you have you have two or more particles, each one of them, it's completely random what you measure, but the information about one tells you basically all the information you need to know about the other particle. This is these correlations, or in quantum mechanical language, entanglement. So it's this complete randomness for one particle, but these very, very strong correlations between particles. And Einstein really, really hated it. I looked up a couple of years ago his publication record, and these his 5 top publications. I'll start kind of from 5 to 1. Some of them are in German. This one is originally in German. This is on gravitational waves. This is basically this theory of gravity, of general relativity, this theory that, moving masses can generate waves. This is what the famous LIGO Observatory has now observed a few years ago. So that's only his number 5 top seller. This one, so Elektrodynamik bewegter Körper, that's special relativity. This is, what overthrew our concepts of time and space, that time is relative, that people, observers in different states of motion will, for instance, measure or not measure simultaneous events in time, that space and time are not separate, as we had believed for many, many centuries, but rather form a 4-dimensional space. That's number 4. This number 3 here is the so-called Brownian motion. It's the fact that if you look at little molecules or little particles, say in water, because this is at finite temperature, the particles are moving around, and that sets the basis of statistics, so-called statistical physics, and many things that we have learned. Number 2 here is so-called photoelectric effect, again in German. So there was a history what happens when light hits on a surface and releases electrons from the surface. The released electrons had properties that could not at all be understood with classical physics. And in fact, this is, if you want, the second paper that started quantum mechanics. The first paper was Planck's idea that light consisted of particles. This is basically the start of serious quantum mechanics. And then his top seller here is, can quantum mechanic description of physical reality be considered complete? It's a paper by 3 authors that we like to refer to in physics as the EPR paradox. In some sense, as I will show you, this paper is wrong. Okay, the viewpoint that it takes is wrong, but it proves something that is very well known among scientists. So, second best way to garner a lot of citations, which are kind of a currency among scientists, to write review papers. So these are unoriginal papers that you write about other people's work, summarizing their work so that the other scientists don't have to read all the original papers. They just read your summary paper. I feel that concept will go away because GPT is getting better. GPT is getting better and better at summarizing things that are not original. And the best way to get a lot of citations, does anybody know what that is? To choose a controversial topic and publish a paper that's wrong. Okay. Because then many people will prove you wrong, and and I can't help but there's a little bit of a component here, although there's also something very serious in Einstein's objections. So this was done 2 years ago. I checked again, well, how is he doing today? So first, I noticed that he has aged, unlike most of us where we. Most of us physicists, we stay eternally young. We have these, gray, kind of, forever young photos on our websites, and as we age. But Einstein indeed aged. Also here, he didn't verify his email. It turns out, although he was at Princeton at the time, obviously. So how is he doing today? Well, first of all, his top paper, increases much more than any of the other papers, right? This is the EPR paradox, many, many more citations per year. He's doing also quite well in terms of the H-index. The H-index was invented by a competitor of Einstein who had many good papers, but no brilliant papers. And so he's doing well, although he's not doing well as well as, for instance, my colleagues Peter Zoller or Misha Lukin, my collaborator, but pretty well. And then finally, no, he seems to be working incognito in Turkey now. So I found that very, very interesting, and I look forward to what else will happen. Yes. So how, for many years, physicists believed, this was published in the 1930s, that Einstein's viewpoint was metaphysical, which means we leave it to the theologians. We cannot really test it until, John Bell came up with a way to test it. And so we will make the system a little bit simpler. So instead of using position and momentum, we'll use the simplest quantum system, which is just 2 levels. There are 2 energy levels often, or maybe 2 polarization states of photons that can have different polarizations or something like that. Now, classically, you're either in this state or that state, so there's just 2 possibilities, just 1 bit of information. Quantum mechanically, however, it turns out that you can be in both at the same time. You can be in one state, or in the other state, or in superposition of the two, so both at the same time, but you can also be in both at the same time in different ways. It turns out the complete way to understand this two-level system is a description on a sphere, where we assign, say, the upper state with a vector pointing up on the sphere, the point up here on the sphere, lower state, the other state with a point down on the sphere. Anything on the equator is a linear superposition, is an equal probability to be in one or the other state, but there's a so-called phase between them. There's a relation, different ways that the particle can be in both states at once, which can be described geometrically by a point along the circle. What is strange about the rules is, yes, the particles are described by the sphere, but when you make a measurement, you don't get, kind of this angle in a single measurement where you are on the sphere. Whenever you measure along any axis, find only two possible values, along the axis or opposite the axis. I'll take that in. It's somehow the particle is in this complicated state, but whenever I measure, I get a digital outcome, either this way or that way. Or if I measure along another axis, same thing, either this way or that way. To garner the full information, I have to measure many, many times. This is where some of the problems of running quantum computers lie. Even if you run a very complicated circuit, in the end, you have to decide along which direction you want to measure. You have to somehow choose the right way of extracting the information from the system. So in this language, what is the EPR paradox? In a spin system, as we said, this paradox always involves two particles. So you can set up a situation where each of these individual particles, you don't know at all where it lies on the sphere, which way this arrow is pointing. No information whatsoever. If you make thousands or millions of measurements on this particle, you will find an equal superposition of all possible directions. No preference whatsoever. However, you can make a state where this particle is completely undetermined, this particle is completely undetermined, but whenever you measure a particle in a certain state along a certain axis, which is completely random, if you measure along the same axis for this particle, you would find the particle to be pointing, say, in exactly the same direction, or in exactly the opposite direction. So these are kind of hard to grasp correlations between measurements. And it also, raises the question, where does the information lie, right? Even if these particles are light years apart, the moment I measure this particle, I know something about that particle that is very, very far away. And this is what Einstein objected to. Now, John Bell, who unfortunately died too early because he would have certainly won the Nobel Prize for this work, he figured out in this context how one can test Einstein's theory. It comes down to that if you measure certain correlations between measurements of the particles, then if Einstein's theory is right, a certain combination of these measurements would always yield a value less or equal to 2, whereas quantum mechanics could exceed this value up to a factor 2 root 2, so up to about 40% or so. And measurements done again and again, and I will show you a few, the first measurements, shown that the quantum mechanics, as is understood, is correct, and this notion of Einstein, at least the notion of local reality, is wrong. It's a little bit like a system where you throw dice and they are kind of, fair dice. They have any side can come up with the same probability, but they are somehow arranged in such a way that they always show the same number. Okay, so both show 1, or they both show 6, or they both show 5. And even if you separate them very, very far away, they still do the same thing. So it's not some direct interaction. It's something about their common past that matters here. So this is a little bit an analogy. People went out to test it. First was John Clauser, who actually, I think, was a postdoc at the time. And he had to do it secretly because his advisor was not interested in this at all and thought this was an uninteresting problem. And so John Clauser figured out a way to make entangled photons, pairs of photons. And then photons can have a polarization, which means photons, as you may know, are electric fields that oscillate. They can oscillate vertically or horizontally or some combination of the two, and so it maps beautifully on this spin 1/2 or 2-level system. So he had a way, I'll show you in a moment, how to make entangled photons, and then he was measuring them in these bases, and indeed he was the first to confirm that Einstein's, or Bell's version of Einstein's experiment showed that Einstein was wrong in his, at least local reality assumptions, and quantum mechanics was correct. How can you make entangled photons? That sounds pretty complicated, to make these photons in a random state, but perfectly correlated. One way to do it is to take an atom in an excited state. So, for instance, you can bombard it with electrons or something, deposit energy in an atom, so an atom is in an excited state. And certain atoms have properties that when they decay down, they do it in a cascaded process. You go from one excited state, the atom emits a photon, and for a certain structure, this photon has a certain polarization. Polarization just means, in this case, the helicity of the electric field of the photon. This helicity can be right circularly polarized or left circularly polarized. So for instance, the atom can emit first a photon that is right circularly polarized and has a red color, and then a left circularly polarized photon that has a blue color. This would be perfectly deterministic. However, the atom, because of symmetry, has also a second path where it first emits a photon of the opposite polarization, the left circular polarizability, and then right circularly polarized blue photon. Now you see, if I just measure the red photons, these two have equal probability, and I will always measure half of them being one polarization and half of them being the other polarization. It turns out, even if I choose a different axis of measuring linear polarization, the same is true. However, as you can see, these photons are perfectly correlated. Whenever the first red photon has one kind of polarization, the other blue photon accompanying afterwards has the opposite polarization. And so that makes the state of strong quantum correlations or entanglement, where each individual photon is completely random, but you have correlations. As soon as you see the red photon, you know what the blue photon will be like. So this was quite ingenious, but of course these photons are produced randomly, so it was not a way to control them. Alain Aspect, who won the Nobel Prize in the same year, 2022, and figured out a way to close a so-called locality loophole. People were very concerned about maybe somehow the information in which basis I had measured this photon traveled over to the other side and influenced my other measurement. So he did this measurement so quickly between distant locations that even at the speed of light, the information could not have traveled. And this is what we physicists call locality loophole, that kind of reality, Einstein's version of maybe information traveling here. And then the third Nobel Prize winner was Anton Zeilinger from the University of Vienna. He pulled off kind of a stunt. He said, well, I'm not going to let a human or a computer set these angles, right? Because maybe they have a bias or something. So he used photons from distant galaxies that had never seen each other, to set it. It's a little bit of a publicity stunt. Of course, it doesn't change anything. Yes, quantum mechanics is confirmed, and things work. He also had a beautiful experiment. You may have heard about teleportation, kind of Star Wars stuff. So usually when photons are entangled, or always in principle, they need to have a common past. Right? The only way to make these correlations is that they originate from some source that makes them correlated. Now, he figured out a way to entangle or correlate photons that had never seen each other. The way he did it is he used two sources. The two blue photons are correlated with one another. The two green photons are correlated with one another. But this green photon and this blue photon have never seen one another. And it turns out that if you make measurements on these blue and green photons together in some smart way, then you can transport the entanglement to the outward pairs. So it's called teleportation because you're kind of transporting some form of information from here to here without ever the two physical systems touching each other. Right? So photons are very nice, but they are kind of randomly produced. They're not very well controlled. They are great for sending information over distances, but to really control information, we would like to have atoms. Atoms are difficult to control initially, but we can make them strongly interact. We can store quantum states for a long, long time, etc. So there was a push to do this. So how do you switch from photons to atoms? First, let me read to you, a remarkable prophetic quote by Richard Feynman from now 40 years ago, from 1983. He said, how we can in principle make a computing device in which the numbers are represented by a row of atoms with each atom in either of the two states, these two-level systems or qubits. Then the Hamiltonian starts. That's just physicist language for something is happening in the system. And then the ones move around, the zeros move around. Finally, a particular bunch of atoms represents the answer. Nothing could be made smaller. Nothing could be made more elegant. Also, any scientist, 10 or more years ago, this would still have seemed, even it's working in the field, as science fiction, but it's remarkable how mostly this picture matches to what I would like to show you. So how to do it? There were two ingredients, and it was kind of very lucky that there were people working at Bell Labs at the same time in the 1980s that had offices very nearby. And one of them was Arthur Ashkin, and he was thinking about the problem. He wanted to trap atoms originally, light beams, but atoms were hot. the light beam traps were not deep enough, the atoms would just escape. So eventually he settled for trapping macroscopic particles or DNA. So if you use a focused laser beam, for instance, it turns out that you can capture DNA, or you can take one of the end of the DNA and tug it and make a knot in the DNA. You can control it. And this was invented by Arthur Ashkin. So he was thinking, I'll show you maybe a movie made by Ted Hench, who also won the Nobel Prize for something else. So this is illustrating interference between laser beams. What you've seen here is 2 green laser beams. This is now 4 directions of laser beams. They form these patterns because waves can interfere destructively or constructively. So they form these patterns. And if you place, for instance, little beads in water, just like Arthur Ashkin did, it turns out that you can use these potentials to influence and trap these particles in water. Okay, so this is possible with particles. Is it possible with atoms? So besides, Art Ashkin, who was working on this, his lab neighbor was Steve Chu, whom you know also maybe as our Secretary of State during the Secretary of Energy during the Obama years. And he figured out a way both laser-cooled atoms and trap them. He was inspired by Art Ashkin's idea, thought about how to laser-cool atoms using laser light. So he figured out how to trap atoms in light beams. At the time, many atoms. You see also there's a big difference. The work was done roughly at the same time, but Steve Chu won this prize roughly 20 years earlier than Art Ashkin, because it was very quickly recognized. This is him, I think, on the day or maybe the day after the Nobel Prize, so quite young looking. I was also very young. I was a young postdoc at the time who had just arrived maybe 2 weeks earlier at Stanford from Germany. This is Cheng Chin, my old friend and now professor at Chicago University. This is Jamie Kerman. He works right now on quantum computing with superconducting qubits. And this is Hazen, a biophysicist. He was basically trapping not atoms, but DNA for some of these experiments. Hazen Babcock. So how do you control individual atoms? So for a long time, we could trap many atoms, but not one. And one breakthrough came now 20 years ago in a remarkable experiment done in Paris. So Philippe Grangier and his team asked themselves the question, what happens if I try to make the laser trap as small as possible? It turns out that a light beam cannot be made as small as possible. There's a so-called diffraction limit. You cannot, because it's a wave, you cannot make it possibly smaller than on the order of the wavelength of light. But he used a very good microscope and focused a laser beam to less than 1 wavelength, 0.9 micrometers or so, or on the order of 1 wavelength. Then he laser-cooled atoms in the same region. He wanted to see what happens. And see, he used the same microscope to collect back light, the atoms while they were being laser-cooled, so scattering light, collect back light and image it onto a camera, and also on a counter of photons. And they saw something remarkable. They saw either an empty trap, or something that was emitting light atom, or if you kind of count photons here as a function of time, this is the time in seconds, this is the photon number in 10 milliseconds, then they identified basically 2 levels. Either there's a low background level, which is basically some scatter light in the chamber coming back out of about 20 photons per second with some variations, or when an atom was present, they measured 3 times that value. What was remarkable, you didn't see something average, but you saw this kind of telegraphic signal, the signal that had just 2 values, and also that the signal persisted for long times, maybe a second or so. So this was quickly understood as having 0 atoms or 1 atoms. And what was even more surprising is the absence of 2 atoms, because whenever something enters randomly, sometimes instead of 1 atom entering the trap randomly, 2 atoms will enter randomly, but that signal was not visible. It was then quickly understood that there is actually a brief moment when we have 2 atoms in the trap, but when 2 atoms enter, it turns out there's a light-induced process that turns them into molecules, and they just fall out of the trap. So basically, whenever this 1 atom disappears, most likely what happened is at this time, second atom entered the trap, and they both together disappeared. And so this was a process where 50% of the time you could have 1 atom, the other 50% of the time 0 atoms. And so problem was this is not scalable, right? If you try to make 10 traps and you want to trap 10 atoms simultaneously, it will be just very, very unlikely that you have all these traps filled. If each one is filled only half of the time, it's exponentially unlikely. And so we picked up particularly Misha Lukin's lab, together with Markus Greiner, we picked up an idea that was around in the community, and that was said, well, if we can see an atom, know that if an atom is there, we should be able to apply feedback and make the system scalable. That was the basic idea. It wasn't really our idea. I'm pretty sure it was around in the community. People just didn't think to try it or thought maybe it wouldn't work. What we did is, compared to Philippe Grangier's experiment, is instead of using one laser beam to trap, we use a certain device that could turn a single laser beam into many laser beams. Here only 3 are shown, but we can make up to 100 or so. Instead of having one trap, we can have 100 traps in this region where the atoms are laser cooled. We then laser cool the atoms to these millionth of a degree above absolute zero, where they start to get trapped, and then we image them on a camera. What you see is that traps are randomly filled. So for instance, this would be a string of atoms. The traps here are not visible, but there's about 100 traps. Each place where you see a bright spot, that's where an atom is. And this is randomly filled. Half of the traps are filled, half are empty. Now, what can you do? You can just take the empty traps and turn them off because they don't contain an atom anyway. And then if you like, you can move the traps containing an atom by changing some electronic signal, or bring them together, for instance. So I'll show you in this movie how we take these strings of atoms and sort them into one-dimensional chain. Now this, suddenly everybody realized now we can do large numbers of particles, potentially quasi-deterministically, simply by imaging them and applying feedback via a computer. This movie is slowed down by a factor of a few. This can be accomplished in about 1/10 of a second. We learned then to do this in 2D and others. So for instance, here's a 2D grid now of atoms, and we can image it and then sort it, and then get, after sorting, these near perfect 2D grids with a few atoms remaining, that basically were not necessary to fill the grid. Again, on the same time scale, we can now make these grids. So we cannot answer how many angels fit on the tip of a needle, but we can answer how many atoms can fit on the tip of a needle. This distance, just for reference, is roughly human hair. Okay, so very, very small. These atoms are packed at micrometer distances. Beautifully, one can also do the trapping in 3D. You can guess where my colleague Antoine Broves comes from. Beautiful structures. They did fullerene-like things, cones, toruses, etc. So one can trap even in 3D. We prefer usually 2D because that gives us nice access along the third direction to address the atoms with laser beams. Now we can prepare atoms. We can make internal states between the atoms, so we can start to think about applications of entanglement. So for entanglement or correlations, we need interactions. We trap these atoms at certain distances, and usually they don't interact at all at these distances. They are a few micrometers apart. Atoms are tiny, very, very small, no interactions. My colleagues, Misha Lukin, Dieter Jacques, Sirac, Zoller, and Ralston had this crazy ideas at about the same time when Philippe Grangier was trapping single atoms, to use a process where you would promote the atoms to a very, very high-lying state. Maybe you remember from chemistry, hydrogen has all these energy levels, many, many of them. Pick a very, very high-lying energy level, where the electron is very, very far away from the nucleus, maybe 10,000 times as far as it would be in the ground state. The ground state atom is 10 to minus 10 meters. An atom in such a state, these are Rydberg state, as I will show you, is 10,000 times bigger, is maybe as big as a micrometer. And then they said, well, if we have these states, it turns out they can strongly interact with one another. This goes back to the work of Johannes Rydberg, after whom these states are named. He looked, this was in the late 19th century, did spectroscopy with lamps on these states and identified them for the first time. Of course, Niels Bohr's famous quantum mechanical model predicted. They were also, extensively studied again when lasers were available by Dan Kleppner at MIT in the 70s and 80s, and Serge Haroche from Paris used them in his Nobel Prize-winning work, so-called cavity quantum electrodynamics, another way to make these highly excited state interact not only atoms with atoms, but also atoms with photons very strong. Now, how does that work? How do we use these to create entanglement and eventually quantum computation? You can think of these atoms having an electron very, very far away, and then there are kind of two limits. One is when the atoms are placed further than a certain characteristic distance apart, which is easily resolvable optically, so say 10 micrometers or so. For reference, human hair is about 100 or 150 micrometers. You place them far away, and then you try to excite them with a laser beam to this highly excited state. You can simply do that. You just tune the laser beam to this particular frequency that matches this transition, and you can put the atoms, both of the atoms, in the excited state. No problem. They are just individuals. However, when you place them closer together than some characteristic scale that is on the order of 10 micrometers or so, something interesting happens. Now, if you excite the first atom to the Rydberg state, you try to excite the second atom to the same kind of excited state, there's a very strong interaction. The atoms, push on another. There's a force between them. In terms of physics, it means there's an energy difference. It now takes more energy, it turns out, to excite the atom to the Rydberg state. So if you excite the left atom, your laser doesn't have enough energy to excite the rightmost atom. But that's a conditional process. Only if the left atom is excited, then the second atom cannot be excited. Instead, because the problem is symmetric, you could also have excited the second atom, in which case the first atom cannot be excited. The statement is you can excite one of these atoms, but not both. And if the system is nicely symmetric, it turns out that quantum mechanics tells you you're in one of these Bell states or these magical entangled states. Either the left one is excited or the right one excited, and you really don't know which ones. Okay? So you can make these kind of entangled states of atoms in now a deterministic way, without waiting for an atom to emit photons. Just by applying laser beams, you can make this entanglement. And so there were beautiful experiments done by Antoine Brouvet and Philippe Granger, and also in Paris, and also by Mark Suffman in Wisconsin, on demonstrating that this could be used actually for the essential ingredient of quantum computation, which is quantum gates. Before I come to that, actually, I'd skip over this. Let me tell you about digital quantum machines. So in classical calculation, we have zeros and ones, and then what we have operations that we call Boolean classical logic, like AND gates or OR gates that can perform computations for you. So to add two numbers, two binary numbers, you can apply a certain set of gates between them to get the answer. Now it turns out that something very similar is happening in quantum mechanics. In quantum mechanics, you're dealing with superpositions. So if both atoms are in, say, the zero state, then they stay in the zero state. If both atoms in the one state, then, say, the second atom flips its state. But everything is possible also in these quantum superpositions. So in some sense, the system realizes many, many possibilities at once potentially if you prepare these individual atoms in the right states. And so then there are kind of two processes that you need to test to make a computer. One is the simple flipping of a bit. You can flip 0 to 1 and 1 to 0. We call these single qubit gates. But in atoms, because they live on the sphere, instead of flipping just digitally from up to down, what you see is oscillations. So as you drive the atom, it oscillates from being all down to being 50% down to being all up, etc. So this is one of the gates that you need. You need to make it with high fidelity so that you have few errors. And then you need also two qubit gates. These are these entanglement gates or the Rydberg gates that make basically the analog of the logical gates in classical computation. And you need also to control them. And right now the field is such that the errors are about 0.5% or so. It turns out this less than 1% error is a magical number. Many different experiments now use these optical tweezers, these ways of trapping individual atoms or molecules for a variety of beautiful experiments. And many of these people are here at the conference. This is a particular beautiful example of two different species, cesium and rubidium. And one is colored in yellow and one in blue, and you can kind of arrange them. This is another kind of the record breaking in terms of the number of atoms. This is, I think, 6,000 atoms or so from a work at Caltech. This is Hannes Berlian's work in Chicago. So the main big problem now remains is quantum computers' errors. Can we fix them? Famous colleagues wrote articles on this. This is Serge Roche, who won the Nobel Prize, very serious scientist. And he had an article saying quantum computing, dream or nightmare. And his conclusion was, therefore, we think it is fair to say that unless unforeseen new physics is discovered, the implementation of error-correcting codes for quantum computers will become exceedingly difficult as soon as one has to deal with more than a few gates. So, there are, very pessimistic assumptions. There are also people who are more optimistic. And And this is the famous thing that, basically we never see the cat being simultaneously dead or alive, or equivalently, we never see a large system that lives in this superposition rather than just being collapsed, being either dead or alive. Now, this is maybe one of the most remarkable intellectual developments in our physics in the last decades. And this is the question whether you can correct quantum errors. In classical information, it's relatively easy to correct errors. Just encode redundantly, you make copies of a bit, say, presented by the two colors, and you say make 9 copies of the bit, and then if errors occur, maybe 2 of the copies will be different. You say, well, the majority is white, so I think white is the right answer. As you make the system bigger, it becomes less and less likely that you make an error in this way. Quantum mechanical, that doesn't work for 2 reasons. One is you're not allowed to look at the particles, because as soon as you look at the particles to identify which state they are in, you're destroying all the quantum magic. The other thing is you're not allowed to make copies either. It turns out there's a famous no-cloning theorem that says you cannot make a copy of a quantum bit without, corrupting it in some way. Nonetheless, it's amazing to me. People came up with schemes how to do it. The basic idea is that you encode things in 2-dimensional grids. Half of these contain data, and half of these are qubits to detect errors. Then what you do is you don't look at the state of the qubit. You don't look whether it's 0 or 1. Just compare the states of neighboring qubits. You ask yourself, are they in the same state or not? Everything went well. All these neighboring qubits should be in the same state. However, if an error occurred, say here, then some of these neighboring qubits that you use for error detection will light up, depending on the type of error. And so basically then you're allowed to look at these other qubits and say, okay, the error must have been here. I'm just going to flip this error without ever looking at it. I still don't know what it was before, and I don't know what it is now, but I can correct errors. And this is a very surprising feat even for quantum scientists. This goes back to the famous work of Peter Shaw at MIT and several other colleagues. This is Andrew Steen at Oxford, and a few other brilliant people have worked on this. So it turns out that we have started to implement these error correcting codes. I will show you now some movies of atoms where we do this. And basically, because we live in 2 dimensions and we can move atoms around, it turns out that we can generate 3-dimensional structures. So for instance, certain codes are encoded not in a surface, but on a torus. And so this will show you a movie now where half of these atoms that will be moving are the data qubits. Then half of the other atoms are the so-called syndrome qubits, the ones that will be detecting errors. Whenever you see a red circle here, it means that a quantum gate is applied, one of these laser beams that makes this kind of logic operation in the quantum world. Strange, okay. Let's see if I can play this movie, yes. So now you see the atoms move, another gate is applied, another gate is applied, another gate is applied, and then there's one gate all the way around, which is to wrap around the torus. And then these atoms are transported from regions. Then in principle, these atoms here, you're now allowed to touch them and look at them, which state they are in. We identify states by looking whether they are bright or dark in an image. Then basically whatever you see here tells you which errors occurred in the system. And so there's a vision to make quantum processors now where you have different regions. You have an entangling zone. You can think of this as the CPU of quantum mechanics. This is the processor where things are happening. Then you have a storage zone. You can think of this as the RAM, the memory of a classical computer where you store atoms. And then basically move the information by actually moving the atoms into these zones. And then there's a readout zone where you can, in the future, detect errors. And you can then encode different codes. And so maybe the last point I want to make is that it turns out that if you want to correct errors in such a system, you have to be below a certain threshold for the errors occurring. Because once you try to correct errors, you need many more particles, you need many more gates, many more processes. And if your errors are relatively big, then by going to that system, you're only going to make it worse than before. However, there's a certain threshold. If you're below that threshold, and you can now implement logical qubits or these error correction codes, then you're going to start to do better. So this is an example where we go from a smaller code to a bigger code, and we see this error ever so slightly decrease by tens of %. But it opens, I think, a new door now where we can start to basically correct these errors. And if you do things right, this will improve exponentially the particle number. Maybe to wrap up, I'll show you actually the most complicated circuit that we have made so far. This has 48 logical qubits, so these atoms are grouped. 8 of these atoms are a redundant encoding of a logical qubit. And then, as you will see, they will be moving around. Gates will be applied to perform a circuit that is very hard to simulate classically. Basically, even on the best supercomputer, if you wanted to predict the outcomes of the experiments, you couldn't do it. And this is, maybe you have heard, Google did the first experiment on something like this. This goes under the name of quantum advantage. For the first time, you can make quantum systems that you cannot possibly simulate, as far as we know, on classical computers. So let me show you this movie. So atoms are moved in certain ways, gates are applied in some patterns. Then, this is kind of the top part of the circuit. There will be soon some more the bottom part of the circuit. Of course, we perform the experiments. We don't actually take movies, right? We do everything in the dark and much faster to show in the movie. But this shows you kind of, maybe gives you an idea how these gates are applied. In some sense, we have arrived at this crazy stage. What do? We collect atoms into a processor, do some calculations. Everything is controlled optically, read it out optically, then we throw away the atoms. Okay, and each time we make it, we throw away this processor. Fortunately, atoms are very cheap. A mole of atoms is a lot of atoms. And so, if you have laser cool atoms, you can easily have 10 million atoms available. So, atoms are basically free. What is costly is the laser beams that are controlling them. And with that, I think I'm running out of time. I would like to maybe tell you where we are. So we do first circuits of error correction. I think you will read more in the news in the next few years. We can scale these systems up to tens to 100,000s of physical qubits. I'm quite sure that quantum computers will be useful for science. Already they're starting now for scientific problems. And we start to get into the realm of serious error correction, where maybe one can perform interesting algorithms that are useful not only to scientists, but to the society at large. With that, I would like to thank you for your attention.
Why would there be, and for the qubit, in microns kind of is a large size, even a particle, why would they, react to each other? Why would they input?
That's a very good question. I repeat the question for the YouTube audience. So the question was, how come that two atoms at 10 microns or a few microns can interact with each other? That's the magic of these very highly excited states. The electron is very far away from the atom. Therefore, when you have fluctuations in one atom, they interact very strongly with the other atom. The reason why we like this stage is because we can only control atoms down to about a micrometer. We would like to place them closer. Because our traps have a certain size, we cannot push them closer than 1 or 2 micrometers. So we need a process that will work over 2 micrometers. And this excitation to the atoms, to the very high-lying Rydberg states, is the answer. That we are solving the problem where we can still resolve the atoms, we can see them individually, trap them individually, but make them interact. It's really the key.
And the second question is the sphere that's being used for qubit state. Is that the Lyman sphere?
We call it a Bloch sphere. Technically, whether it's the same, I don't know. I'm not familiar with that language, but it's, for the mathematically minded, it's an SU2 representation of certain mathematical properties.
Does that imply that you have a single laser beam for every one of the atoms?
That's exactly right. We have
Array of beams?
Yes.
One source.
Yes. So I will repeat. So the question doesn't mean you have many laser beams. Yes, we have one big laser beam that goes into these magical devices. You can think of them as an LCD projector, right? An LCD projector also has 1 million pixels or so. So we use some of this similar technology, just we need it to be much, much faster. And so you send in a single laser beam, you create 1,000 traps that you can control, and then you load atoms.
Move them to superimpose.
Yes, you move them to superimpose. That's by basically changing the pattern. So you control this with certain electrical signals that can move these laser beam traps around. That's exactly right. Mm-hmm.
Look, the atoms, what kind are they? What kind of mass do you look for? And then how do you get a laser that's photons, right? No mass. What about the laser? Can it be adapted to control a mass?
Very good question. So the question is, which atoms, how do we choose them, what mass, and, how do we choose or adapt lasers? These atoms are at very, very low temperatures, colder than, any cryostat, but the atoms are cold. So the atoms have to have certain properties that we can cool them with laser beams. It means they have to have a certain relatively simple electronic structure. So typically we use so-called alkali atoms. For those who remember chemistry, the first column in the periodic table, they are simple because they have just one valence electron, one outer electron, and they have a very simple spectrum. People have pushed this now to 2 electron atoms, and of the second column, the chemistry table, the periodic table. So we need very simple atoms that have transitions that make them amenable. That's how we choose them, but there's maybe a dozen or at least a half a dozen possible choices, and there are currently 2 front runners. We work with rubidium atoms, other groups prefer which is a 1 electron, 1 outer electron atom, other groups work with 2 electron atoms. It's not only the atoms that matter, it's also the availability of laser sources. We need very high power lasers that are also very, very stable in frequency. They need to have very special lasers. So we're kind of almost needing lasers that are used for welding, but that are, as precise as the most precise clocks or lasers that we can imagine. So that excludes certain atoms simply because the laser sources are not available. For instance, UV lasers are very hard to get, so we use lasers in the visible infrared. So it's these 2 combinations, but in principle, it can be done with many atoms. Good question.
Just like a little more about what is the gating function, and just a little more about the MID.
The gates, the logical gates?
How does it work?
Very good questions. The question was about gates. So it turns out that in classical logic, you can build anything complicated like multiplication, addition, whatever process you want, out of logical gates, out of a small set of logical gates. Say the NOT gate where you just flip bit, or the AND gate, for instance, which just has an outcome. You put 2 of information, what you get out. It turns out that quantum mechanics or quantum computers has a similar theorem. The very small number of gates can make any other more complicated process possible. So basically, you're trying to create these native gates, and there are 2 of them with some, basically just the ones that I showed, namely that you rotate a bit from one state to the other by an arbitrary amount, or that you make a certain site where you say flip the state of one bit conditioned on the state of the other bit. These are the native gates, and then it turns out you can do everything else that you want with it. And physicists have thought about many different ways to make these quantum gates. There was a question there, and then there.
Jensen Huang, the CEO of NVIDIA Corporation, recently stated that quantum computing is like 10 or 15 years away, and that, of course, tangled the quantum stocks. But what I'm really curious about is how far is quantum computing from being useful, and what are its best use cases?
It's a very good question. So, people are skeptical that it can be done in near term. There are predictions 10, 15, 30 years. What are use cases? How close is it? A few years ago, I would have said it's many years away. We have made, as a field, many different fast breakthroughs earlier than expected. For instance, these first error correction methods believed to not happen before 2030. We had them in 2024. So it's very hard to predict. In terms of use cases, there's one proven case where we know quantum algorithms work. That's the famous Shor's algorithm that breaks the currently used encryption. That we would need enormous large quantum computers that are not yet on the horizon. For me, most likely evolution of the field will be similar to AI. The concepts for AI, like neural networks, were developed already in the 80s, but the hardware was just not yet ready. Then for me, the first moment was when Deep Blue beat Kasparov in chess games, because we believed strongly, only humans can play chess, right? And then we said, okay, maybe something is happening. And then it took a number of years. There was a few more developments until we are where we are right now, where you can ask serious questions of some of the AI machines and get reasonable answers. I think we will see a similar evolution, but exactly on what time scale? I think within a few years we will see something that will convince us that it's possible to make useful quantum computers. That's my personal prediction.
Excellent. To our question, firstly, how does entropy apply to the practical applications of quantum entanglement or the issue that I try to compress electricity to quantum states as most data is like it's possible quantum battery.
Okay, very good questions. Although there were several. One is, what is the role of entropy in the system? The second is this related to electricity? And then, can you make batteries and so on? So the entropy question is easiest to answer. When entropy is a measure of disorder, these errors in quantum computers happen. They create entropy or disorder. What these error corrections code do is they take that entropy, put it into the system that you're pulling out. So these error corrections constantly trying to pull out entropy out of your quantum computer to keep it in this pristine state. So that's very easy. In terms of electricity, people have done experiments with atoms that model electricity, especially superconductivity. There's frictionless, dissipation, less transport of energy. It would be great if we could do it at room temperature, for instance, right? That would revolutionize things. People have done experiments, scientific experiments modeling that, but they haven't solved yet the riddle of superconductivity. And then quantum batteries, there's a lot of, at the moment, theoretical work saying, if we had quantum mechanical versions of batteries, how would they be better than the current ones? And I would say that's, an open field of research. What that even means.
What is the largest distance you can separate tangled atoms?
In our systems, it's given by, so we have a microscope objective that can focus a certain area. So we have done experiments of a couple of 100 micrometers. You can basically, it's expected you can move them as far as you can move these laser beams. It's not really limited by the atomic properties, but our ability to control the laser beams over a certain distance.
Separate?
Yes, you can trap them and separate them. This brings up a certain interesting question. In the future, at some point, we will run out of space. We will have to build quantum computers of the future that are modules. For that, we need to separate entanglement. There are various ways how one can either separate entanglement or create entanglement non-locally. It's a little bit like the teleportation experiments. If you take two atoms at a large distance, make their photons interfere, you can entangle the atoms. Those experiments have actually been done in work and at the University of Maryland at the time of Chris Monroe with meters to hundreds of meters distance.